బాబు కెమిస్ట్రీ రాసుకో కోటేశ్వర వచ్చింది కమన్ కెమిస్ట్రీ వచ్చింది కెమిస్ట్రీ
ఏం యశ్వంత్
చేంజ్ అయింది రైట్
అటెండెన్స్ తీసుకుంటున్నారా?
కోటేశ్వర్ సార్
రాజు రాజు reaction mechanism. Intermediates.
అవును
Yes. So, carbonates. Previous class. Radicals. Yes. Yes, dear students. Right. Dear students, we are covered discussion about the carbocations, carbanions, and free radicals in the previous class. Now I'm going to start the carbenes. This carbene structure is like that. The carbon, which is shown like a divalent. It is attached with two sigma bonds and a pair of electrons and one vacant orbital. This is a general methyl carbon structure. Then formation of carbon. How the carbon is generated? By cycloelimination reactions. Cycloelimination reactions. In this reaction, phenyl cyclopropane, phenyl cyclopropane on irradiated with light, it homolytic cleavage of these bonds, carbon-carbon bonds, that leads to formation of a carbene. Simultaneously, one unsaturated styrene-like product is generated. Now here, in this derivative, this is the aromatic compound. There is a bicyclic six-member and three-member is fused with the two phenyl groups. A common sigma bond is there, which is on irradiated with light. The carbon is formed from these two sigma bonds, CC bonds, by undergoing the homolytic cleavage. Then it leads to formation of phenanthrene and carbon. Next, third one, 3,3 dimethyl hydrazine. This 3,3 methyl hydrazine, dimethyl hydrazine, on irradiations, and sometimes it also eliminates the nitrogen gas on heating also. Okay, this is also produces dimethyl carbene. Next, from diazo compounds, a diazoalkane, which is on photochemically irradiated, or we are subjected to photochemical conditions, that leads to formation of carbene, alkyl carbene, along with elimination of nitrogen gas. And the next example, this is diazocyclohexanone, diazocyclohexanone. It will generate very easily. Two amino cyclohexane is there, which is treated with the HCl followed by so NaNO2. That leads to formation of alpha diazocyclohexanone, which is on photoirradiation. That leads to formation of a carbene. The carbene intermediate is generated on the carbon of cyclohexanone. Next, from ketenes. This is a ketene, C double bond C double bond O. It is actually an intermediate. This intermediate undergoes decarbonylation, CO removal from that molecule. That means a pi bond and sigma bond between the CC bond undergoing the homolytic cleavage, that leads to the formation of this carbene and carbon monoxide. Next, from carbon ions. Carbon ions means generally this kind of reaction occurred with the chloroform. Chloroform is untreated with sodium hydroxide or potassium hydroxide. First, it is undergoing the elimination of water, and then it forms a carbon ion, that is a CCl3 minus. That is a carbon ion. That carbon ion is on again treats with the proton, that eliminates the HCl, followed by liberation of dichlorocarbene. And other examples. Next, structure of carbene. This carbene exists in two states, two excited states. One is the singlet state and another one is the triplet state. That is purely depends on the electrons arrangement in the unhybridized p orbital and hybridized sp2 hybrid orbital. Now, two electrons are filled in only sp2 hybrid orbital. Unhybridized orbital is vacant. That is in the form of singlet state. Look at here. This is the carbon. It is the sp2 carbon. In this carbon, look at here. This is the unhybridized p orbital. This is the sp2 hybrid orbital. The two electrons are filled in the sp2 hybrid orbital. The unhybridized p orbital is vacant. Now here, when you consider a pairing of the electrons, it is a spin pairing is generally appear here in the case of singlet state. Therefore, the sum of the spins of the electrons is zero, sing one. That is calculated with the s into s plus one, s into s plus one, or n plus two by two formula. Okay. Now coming to triplet state. Here the triplet state, the carbon may be exist in two hybrid forms. One is the sp2 hybrid form and another one is the sp hybrid form. If the triplet is in the hybrid sp2 hybridization carbon, that is a bent structure. That bent structure is appear like this, right? In this bent structure, if you see that the unhybridized p orbital is perpendicular to the plane and perpendicular to the plane, and when you pass the plane, it is passing through only sp2 hybrid orbital, and the remaining two sigma bonds above and below are arranged. Above and below are arranged. Therefore, this is the triplet carbene, a bent structure, and a triplet carbene with the sp hybrid carbons. S right. A triplet carbene is it is in the linear form. The carbon is existing in the sp hybridization. That means the carbon is existing with two unhybridized p orbital. Those two are perpendicular to each other. Okay. In that case, if the carbon is sp hybridization, the attached two sigma bonds are linear. With that kind of linearity we generally see in the alkynes. Okay. Similarly, the carbon alkyne will show the linear structure. Similarly, the carbon which is existing in the sp2 hybrid carbon, and that is existing in the linear structure form. Next, reactions of carbene. Carbenes involving a diverse range of reactions. In that first one, cycloaddition reactions. In that cycloaddition, olefins are undergoing cycloaddition with the carbene that leads to formation of cyclopropane. A simple olefin double bond is undergo addition reaction that leads to formation of a cyclopropane derivative. Similarly, if you take cis-2-butene is undergoing cycloaddition with the singlet carbene that leads to the formation of cis 1, 2 dimethyl cyclopropane. 1, 2 dimethyl cyclopropane. And next, trans 2 butene. The trans 2 butene is also producing trans product to trans 1, 2 dimethyl cyclopropane addition product. Next, cis-2-butene with a triplet carbene. It leads to the formation of a triplet diradical. The triplet diradical CC sigma bond is undergoing rotation for getting stability, and it will be interconvertible. Cis biradical is converting into trans biradical is converting into cis. That leads to for other reaction by the spin inversion that leads to formation of cis and trans products in the 50-50%. That means if you conduct the reaction only cis 2 butene, that leads to formation of 50% of cis product, 50% of trans product. Similarly, that is happen in the case of trans 2 butene also. The resulted product is cis product and trans product in the 1:1 ratio. Whether it is the cis reaction is cis 2 butene is the starting material, or trans 2 butene is the starting material, or mix of these two gives the equal ratio of the product. Next, insertion of the CH bond. Insertion into a CH bond. Simple alkanes. Simple alkane is treated with the singlet carbene that leads to formation of a three-member intermediate or transition state. This transition state for other produces to substituted product. Simply, this carbene is inserted between these two carbon and hydrogen bond. Then that leads to the formation of radicals. Further, it is involving, suppose instead of singlet carbene, it is involving triplet carbene. That is generating this product. These two radicals will be generated. Again, these two radicals are combined together. That leads to formation of this product. In both the cases, the product formation is similar kind, but the mechanism is different. Okay. Next, reaction with the nucleophiles. Reaction with the nucleophiles. Uh, this is the methanol. It can able to donate a pair of electron. Then it is donated to the carbene. It is having the vacant orbital. To that vacant orbital, this pair of electron donated to this carbon that leads to formation of carbon-oxygen bond. Simultaneously, after donation of this pair of electrons, the oxygen gets the positive charge. This positive charge will be neutralized with the elimination of the proton. Then that leads to formation of ether product. Right, phenoxide ion. Whenever phenoxide ion is involving, the phenoxide is rearranged to produce a carbene ion in the aromatic ring. That is involving nucleophilic simple donation of this negative charge to the vacant orbital of the carbene. That leads to the formation of carbon-carbon bond. Further, it is undergoing to produce salicylaldehyde. Right. It is generally seen in the case of trimer-trimer reaction. Next, rearrangement reaction. That rearrangement reaction involves alpha diazomethyl ketone, which is on heating, it eliminates the nitrogen that leads to the formation of a carbene. The carbene further undergo rearrangement that leads to the formation of ketene. That ketene is the product. For generation of the ketene in the reaction, it is very helpful tool or helpful reaction. Next, cyclopropyl carbene. Cyclopropyl carbene is further rearranged to cyclobutene. Similarly, this is undergoing the ring opening reaction that leads to formation of cumulene is generated. This is the cumulene, C double bond C double bond CH. Okay. Next, nitrites. The formation of nitrite. Before going to the nitrine, yes, the nitrine intermediate contains a monovalent nitrogen having a six-state electronic configuration or six-state electrons. That simply we can show that RNH2, RN, that is nitrine. Acyl nitrines are the intermediates in Hoffman, Cartesius, Lawson's, Schmidt rearrangement reactions, right? And now, how to form or how to generate the acids? How to generate the acids? Acids can be, nitrins. Nitrins can be generated from the acids. This acid is on heating, a simple heating reaction, or sometimes it is irradiated with light that leads to formation of nitrine. Here alkyl group may be, here R group may be alkyl, aryl, azido, or azide, cyano, alkyl amino, or carbethoxy groups from N-aryl sulfonates of amines. N-aryl sulfonates of amines. N-aryl sulfonates of amines is treated with base that eliminates the one proton from the molecule from the nitrogen that leads to the formation of negative charge on the nitrogen. This nitrogen further cleavage of nitrogen oxygen bond. That means heterolytic cleavage. The nitrogen oxygen bond pair is completely taken by the oxygen. Then it leads to formation of aryl sulfonic acid along with the nitrine. From ortho-aryl hydroxamic acid. From aryl hydroxamic acid. Ortho-aryl hydroxamic acid. This is the acyl hydroxamic acid, right? Yeah, this R group may be sometimes aryl group. We can treat it as ortho-aryl hydroxy acids, right? Which is treated with base again. It leads to formation of negative charge and nitrogen. Then it leads the dissociation similar to the previous reaction that leads to the formation of nitrine and some acylate ion, yes, yeah, acetate ion, right? Next, structure of nitrine. Here, you consider that nitrine is existing in two forms. One is a singlet state, and another one is a triplet state. In the case of singlet state, singlet state, the singlet nitrogen is existing in sp2 hybrid form. sp2 hybrid form. Like a carbene, nitrine may be in the singlet or triplet state, just similar to the carbene. In singlet nitrine, the nitrogen is in sp2 hybrid state, whereas in triplet nitrine, it is in sp hybridized form, very much similar to the carbene. A triplet nitrine is more stable than the corresponding singlet state. The ground state of the most nitrine is probably triplet. Then they can be generated in both the states during the reaction. You can generate both the states during the reaction. Now, what are the reactions of nitrine? Addition of addition to the multiple bonds, addition to the multiple bonds. Then nitrine is an addition to the olefin that leads to formation of three-membered as aziridine is generated. Aziridines are the products. Aziridines. These aziridines are nitrogen three-membered and the smallest membered nitrogen heterocyclic compounds. Next, it is treated with benzene, sulfonyl nitrine. This sulfonyl nitrine first undergoes the addition reaction to the pi bond in the aromatic system that leads to the formation of a sulfonylamide is the product. This is the mechanism again. Carboxy carbethoxynitrine. This carbethoxynitrine is treated with the benzene. First is these undergoing the donation of this pair of electron to this carbon. Simultaneously, these pi electrons are donated to the nitrogen that leads to formation of three-membered ring. Now, this will be rearranged to produce a seven-membered azepine derivative heterocyclic compound. Azepine, 1-carbethoxy, carbethoxy, azepine. Next, olefin. This is the alkyne. Alkyne is also undergoing the addition with the an amino nitrine that is leads to the formation of two azerines, a two azerine, which is further dissociated or rearranged to produce one one azerine. Next, dimerization. Aryl nitrine undergoes dimerization that leads to the formation of azoarenes. Insertion into the CH bond. Insertion into the CH bond. You take it is very much similar to the reaction with the carbene. Carbene is also undergoing the insertion reaction with the CH bonds. Here, the singlet nitrine is also undergoing the insertion reaction that leads to the formation of a transition state, three-member transition state. This three-member transition state further undergoing cleavage that leads to formation of amine derivative. Now this is the nitrine again. It is treated with the on heating. It is eliminated. Actually, it is N2. This N2 is eliminated as nitrogen gas that leads to formation of nitrine intermediate N single bond NH2. Just like here, this is existing like that. N triple bond N. Yes, which is on heating. This nitrogen is eliminated from here. Then it leads to the formation of aryl nitrine. This aryl nitrine further undergoing the cyclization, the donation of this pair of electron to this place. It is undergoing a carbon hydrogen insertion reaction. Now this sigma bond hydrogen is migrated to here. That leads to the formation of 2-methyl, 2-ethyl indole. Right. Next, hydrogen abstraction reactions. Here Triplet nitrine is reacting with the alkanes. It is undergoing the CH bond dissociation. This hydrogen will be abstracted with this triplet nitrine that leads to the formation of this NH nitrine like derivative. Then it is further undergoing reaction with this radical. Again, another hydrogen is abstracted from the another molecule of this alkane that leads to formation of an amine radical is generated. These two radicals are combined together that lead to formation of extended carbons containing alkane. Next, rearrangement reactions. The rearrangement reactions. This is the nitrine, a secondary alkyl nitrine. This is undergoing the rearrangement of this R group is rearranged. That leads to the formation of amine derivative. This is the amine C double bond N derivative is called amine derivative. Similarly, this one also cyclohexyl alkyl nitrine, which is also undergoing the rearrangement that leads to formation of an imine.
నువ్వు అప్పర్ రైడర్ నీ ఎత్తావు నువ్వు లేవా డివైడ్ వర్క్ అంతా ఎటువంటి చేస్తే మీరు వర్క్ షాప్ ఎందుకు లేదు
Right. Next to intermediates, arynes. Arynes. This is the actually the benzene is substituted with the NH2 or chlorine like substitution. Whenever we are eliminating HCl or NH2, NH3 from the benzene, substituted benzene that leads to formation of benzene derivative. These benzenes are dihydrobenzene is the parent arene. Arenes are the intermediates in the nucleophilic substitution of non-activated aryl halides. Non-activated aryl halides. Non-activated aryl halides like aryl halides without activating groups like NO2 cyanide groups or nitrite groups in the presence of strong base like sodium diethyl amine. How they are formed? Formation of arynes from non-activated aryl halides. This is the chlorobenzene. The chlorobenzene is treated with sodamide in the liquid ammonia at minus 10 degrees centigrade. It is undergoing the elimination of minus hydrogen halide. It is leaving from the molecule that leads to the formation of benzene. And orthochlorotoluene. This orthochlorotoluene is treated with sodamide that leads to the formation of 3-methylbenzene along with the elimination of HCl. Orthofluorobromobenzene, both are undergoing elimination reaction that leads to the formation of benzene. Next, similarly, halonaphthalenes. Here, halo means X may be a chlorine, bromine, or iodine, or fluorine also sometimes. Is treated with the sodamide, NaNH2, at a lower temperature that leads to the formation of 1-naphthalene. This part of molecule is the benzene intermediate. This part actually C triple bond C. Okay, and also it is very unstable one. It is undergo further reaction. Generally, it is prepared as in situ in the reactions from ortho-disubstituted benzenes. Substituted benzene, anthranic acid. This anthranic acid is treated with the uh, nitropentane in THF that leads to the formation of diazotization in presence of H plus that leads to the formation of diazo derivative. The diazo derivative is undergoing rearrangement that leads to the formation of elimination of nitrogen and HX. Actually, this one is Na-NO2 actually. Okay. Next, orthodiiodobenzene. Orthodiiodobenzene is on photochemical condition or on pyrolytic condition. 500 degrees centigrade degrees are generally known as pyrolytic conditions. Or in the presence of light that eliminates the iodine from the molecule that leads to the formation of benzene. A simple benzene is generated. In the iodophenyl mercuric chloride or mercuric iodide, iodophenyl mercuric iodide is on photochemical conditions. It leads to the formation of benzene. Next, from derivatives of phthalic acid. This is the phthalic acid, phthalic anhydride. Okay, phthalic anhydride is on heating at 600 degrees centigrade or at photolytic photo conditions. It leads to the formation of carbon dioxide and carbon monoxide that lead along with the benzene intermediate. Next, thalloyl peroxide. This is the thalloyl peroxide, CO bond O, on photochemical condition or at a heating at 77 Kelvin eliminates the two carbon dioxide molecules along with the benzene. Next, from benzofused heterocycles. Benzofused heterocycles. This is the 1-amino benzotriazole. This is a triazole derivative, and at the first position, amino group is substituted. This is 1-amino benzotriazole. It is treated with the lead tetraacetate, that is the oxidizing agent. On oxidation, it leads to the formation of a nitrogen intermediate. This nitrogen intermediate on heating, nitrogen gas is eliminated. Two molecules of nitrogen, one from here, one from here. They are eliminating. That leads to the formation of benzene. Next, on photochemical conditions, benzo 1, 2, 3 thiazole 1, dioxide. This is a thiazole dioxide derivative, which is on heating that leads to not heating. Under photochemical condition, it eliminates the nitrogen gas as well as sulfur dioxide along with the benzene. These are the preparations. Now coming to the structure of arenes. Structure of arenes in the acetylene structure. We treat yes, we treat it. C triple bond or C triple bond R C triple bond C R. This is the acetylene derivative, acetylenic bond. Up to this, we call it as acetylenic bond. Okay, this acetylenic bond is existing in this benzene, like right. In the benzene, three bonds are there. Similarly, right. Now, this benzene is having acetylenic structure. This acetylenic structure generally linear. But in the case of benzene, this acetylenic structure of a benzene intermediate may not be possible since two triply bonded carbons and two atoms directed attached to them should lie on the straight line, just like this. Just like this. Most probably, the new benzene is formed by the overlapping of sp2 orbitals belongs to the neighboring carbon atoms. Neighboring carbon atoms. That is the only possibility to generate the carbon ions because it is the only assumption. C triple bond C is the only assumption. If it is C triple bond C is generated, that should be a linear structure. But in the case of cyclic compounds, the linear structure formation is not so easy. Okay. Then next, detection of arynes. How these benzenes are detected? Benzenes are undergoing a dimerization by cycloaddition reactions that leads to the formation of biphenyl Biphenyline is the biphenyline, and this is the compound by which you get here. This is the benzene is undergoing the addition reaction with the furan. Then it leads to the formation of this kind of addition product. And if it is addition with the anthracene, it leads to the formation of tri- triptylacene. Addition product is generated. Triptylacene is generated. Okay. Next, reaction with the nucleophiles. Reaction with the nucleophiles. It is reacting with ammonia. That leads to the formation of addition of ammonia on the triple bonded 5 bond. Then it leads to the formation of aniline. In the case of piperidine is undergoing addition reaction with the benzene. It leads to formation of addition product. It may lead to the mixture of products, that is 68% is the alpha substituted product and 32% is the beta substituted product. This is the alpha position and this is the beta position. Next, benzene. Benzene is reacting with the trityl carbon ion. Triphenyl carbon ion. This triphenyl carbon ion is undergoing addition on the benzene that leads to the formation of a substituted carbon ion is generated. That phenyl carbon ion is generated. This phenyl carbon ion further abstract the proton from the source. Then it leads to the formation of triphenyl carbide or triphenyl methyl benzene or tetraphenyl methane. You can call it as tetraphenyl methane. Similarly, phenoxide addition leads to the formation of this carbon ion. Further, it is abstract the proton. Then it leads to the formation of diphenyl ether. Diphenyl ether is the product. And similarly, thioether, diethyl thioether is undergoing the addition on the benzene that leads to the formation of that addition product. Later, this carbon ion abstract the proton from the ethyl group of the that thioether derivative substitution. Then it leads to the formation of a rearranged product by the elimination of ethylene from the molecule. Next, cycloaddition with the pentanone derivative 1 comma 2 comma 2 comma 3 comma 4 comma 5 tetraphenyl cyclopentanone that leads to the formation of addition product and followed by elimination of proton that leads to the formation of tetraphenyl substituted naphthalene is generated, and addition with the acetylene that leads to the formation of a cyclobutanone fused benzene ring is benzene system is generated. Addition with the triphenylamine on reaction with the benzene that leads to the formation of 1-phenyl benzonitrazole, and next to it is reacted with the PHCNO, that is the phenyl phenyl cyanate that leads to the formation of 3-phenyl 3-phenyl benz isoxazole, 3-phenyl benz isoxazole derivative. Next, electrophilic addition reactions. It is undergoing electrophilic addition reaction with the trialkyl borine that leads to the formation of borine substituted phenyl or benzene derivatives, aromatic derivatives. Okay, these are about the intermediates. Now coming to the elimination reactions. Just wait, I will change the presentation. Yes. Okay. Now coming to the rearrangement reactions, molecular rearrangement reactions. In this rearrangement, whatever the intermediates till now we have discussed in the previous class and today's class, several rearrangement reactions are involved in these intermediates. Based on these intermediates, we are going to discuss for some rearrangement reactions here. Now, the term molecular rearrangement refers to the migration of a group or an atom from one atom to the another atom, or from one position to the another molecule within the same molecule, is known as rearrangement or molecular rearrangement. In a molecular rearrangement, generally the molecular skeleton of the substrate changes, undergoing changes. That means, suppose one group or an atom from a position, first position or second position or third position, it is migrating from its position to the migration origin to migration terminus. Then it leads to the formation of structural change. That it means skeletal changes it is undergoing. That is known as molecular rearrangement. The molecular rearrangements usually involve one to shift, or sometimes longer shifts maybe takes place. That depends on the stability of the intermediates generated in the molecule during the reaction. Generally, one to shifts are very common. That shifts, if you consider that shift, in this condition, the molecule primarily existing position is known as migration origin. Like here, the group, which is the group is undergoing the migration. The migrating group or atom is existing at position A. Now that is called migration origin. Migration origin. That means suppose we are moving from one position to the another position. Suppose I am moving from my home to office. My office is the terminal. My origin is my home. Like that here group, whatever the group is present in the molecule, is undergoing migration, the initial position is called as migration origin. After migration is completed, wherever it is reached, that position is called migration terminus. That is called as terminus. B is the terminus. Okay, where G is the migrating group and A is the migration origin, B is the migration terminus. B is an electron deficient. Migration here, migration is several types. Depends on the migration mechanism. Suppose if the migrating group, suppose the B is the electron deficient, B is the migration terminus. From A to B, it is moving. Whenever it is moving, the B is the electron deficient. It cannot able to provide a electron dense to establish the bond. In such case, the A is migrating with its sigma pair of electrons. Now, that kind of migration is called anionic or anisotropic or nucleophilic rearrangement. That arrangement is called anionic or anianotropy or nucleophilic rearrangement. On the other hand, if the B is the electron-rich position, it can able to donate a pair of electron or density. Then G is undergoing migration without its sigma pair of electrons. Then a positive charged species migrating from A to B. In such case, that migration is called as catianotropy or electrophilic rearrangement reaction. Suppose sometimes it is undergoing with free radical rearrangement. That means A and B both are having same polarity. Same polarity. That position is neither having excess, neither having deficient. In such case, the group or atom is migrating with its electron, which is present in the sigma bond, is carried and migrates. That is called radical migration. That nucleophilic rearrangement are more common, but this rearrangement is called free radical rearrangement. That kind of arrangement is called as free radical rearrangement or radical rearrangement. In overall rearrangement reactions, nucleophilic rearrangement reactions are more common. The molecular rearrangement may be intramolecular or intermolecular. Intermolecular. That means in some reactions, the migration of group takes place from one position of the molecule to the other position of the same molecule. That is called intramolecular rearrangement. Intermolecular rearrangement. Intramolecular rearrangement means the migration is taking from one of the position of the one molecule to the one other position of to the other molecule. Okay. Intramolecular rearrangement shift, the migration groups never become the free from the rest of the molecule. In the intramolecular rearrangement, that means the group is completely not detached from its origin. At the same time, it establishes the partial interactions with the migration terminus. Such kind of migration is known as intramolecular rearrangement. It is completely not detached from the molecule during the migration. In the intermolecular rearrangement means the migrating group is or atom is completely detached from the migration origin of the molecule to the at the same time it establishes the new bond with the migration terminus in the new molecule, another molecule. Okay. Generally, this can be understood by the intermolecular rearrangement undergoing the dissociation of the molecule and recombination of the dissociation and recombination mechanism is followed. Now, the Mervin founder of rearrangement, phenol-phenolone rearrangement, acid-catalyzed rearrangement of carbonyl compounds, Demisenous rearrangement, Wolff rearrangement, Beers-Williger oxidations, rearrangement of peroxides in the presence of acids, and transcellular rearrangements are some examples for the nucleophilic rearrangement reactions. Now, coming to the Wagner-Mervin rearrangement. This is the Wagner-Mervin rearrangement. It is catalyzed with the silver metal in it interacted with the halogen present in the alkyl group. Then it leads to the formation of AgCl. A carbon ion is generated. Carbocation is generated. That carbocation further undergoing the rearrangement that leads to the formation of a stable carbocation. Then the stable carbocation react with water, that leads to the formation of alcohol, or it is undergoing the elimination from the eliminates the hydrogen H plus ion from the molecule, that leads to the formation of olefin 2-methyl butene and 2-amyl tertiary amyl alcohol is generally generated. Okay. This neopentyl rearrangement is the simplest example of Wagner-Merwin rearrangement. The driving force for this reaction formation is more stable carbocation. For an instance, during the reaction, the majority of methyl groups lies equidistant from the migration source and migration terminus. For example, here you take the tertiary carbocation, or if you consider this is a cyclopropyl group, it is 1,1,2-methyl dimethyl cyclopropyl carbocation. Next, another example, 3,3 dimethyl butanol. Butanol in the presence of acid, dilute acid, that leads to the protonation of OH group. Protonation of OH group. That protonated OH group will be eliminated as water. Then that leads to the formation of carbocation. This is the secondary carbocation. Now the CH3 group, which is with its pair of electron, is undergoing migration. It is undergoing rearrangement from secondary carbocation to tertiary carbocation. It is rearranged. Then a stable carbocation is generated. This is called 1,2 shift. If we label it 1, 1, 1, 2, from one position to second position it is moving. That is called 1,2 shift. Then it leads to the formation of tertiary carbonium ion. This tertiary carbonium ion further undergoing the addition of water, that leads to the formation of alcohol, or elimination of proton, that leads to the formation of highly substituted product. Highly substituted product. Right. Right. Wagner-Merwin reactions of the camphenyl hydrochloride. Camphenyl hydrochloride. It is the when you are using a polar solvents, then the CCl bond is undergoing cleavage, that leads to the formation of carbocation. Then the sigma bond is undergoing the migration, sigma rearrangement, that leads to the formation of carbocation. Now it is the tertiary carbocation here. First it is generated tertiary carbocation and it is secondary carbocation. Right. Maybe the leaved chlorine may be undergoing addition, undergoing substituted here. That leads to the formation of the chloro substituted product, but it is somewhat disturbed. That leads to the formation of isopharmyl chloride. From camphenyl hydrochloride is rearranged to isopharmyl chloride. Phenol-phenolone rearrangement. This is a very well-known reaction. The acid catalyzed rearrangement of phenols that leads to the formation of phenolone involving the rearrangement of carbonium ion. The conversion is generally carried out in the presence of strong acid. If you consider the example, that phenol-phenolone rearrangement, this is the phenol. Simple ethane is substituted with on each carbon OH, CH3, CH3, or 2 comma 3 dimethyl 2 comma 3 dihydroxy N butane, that is known as phenol, which is on treating with acid that leads to the formation of phenol. The mechanism is which is on treating with the water, it abstracted, the OH group is abstracted as proton. Protonation is takes place. On protonation, it is undergoing the cleavage with the sigma bond pair of electrons. This sigma bond pair of electrons is taken by this water molecule that leads to the formation of elimination of water and along with the carbocation generation. After formation of this carbocation, it is undergoing the rearrangement. The methyl group is rearranged to the third position to second position. That leads to the formation of this carbon ion, this carbocation. This is the more stable carbocation because here, however, it is the plus inductive effect of methyl group. Whenever this positive charge is moving to this carbon, the OH group is having two lone pair of electrons. They can able to donate that pair of density to the carbon electron deficient carbon to get more stability. Then both are undergoing both are in equilibrium. Both are in equilibrium of this stage. Later, elimination of one proton that leads to formation of phenol. Right. When the rearrangement is carried out in the presence of isotopically labeled water, the reaction is stopped before completion. The recovered phenol is found to contains O18 isotope. This is suggests that the reversible formation of carbonium ion is observed. Further, the bromohydrin and the aminohydrin capable of forming the same carbonium ion also yields phenol. For example, the bromohydrin is treated with the silver ion. Then that leads to the formation of carbocation. This carbocation is also generated by the aminohydrin, which is treated with the nitrous acid by the elimination of nitrogen gas that leads to the formation of same carbocation. This carbocation is undergoing the rearrangement that leads to the formation of this more stable carbocation or carbonium ion that leads to the formation of rearrangement by the elimination of proton leads to the phenol derivative. These are called semi-phenol rearrangement. Whatever these reaction involved, bromohydrin and aminohydrin involved reactions are known as semi-phenol reactions. It seems like that the migration of the alkyl group is extremely rapid. After the loss of water or bromide ion or nitrogen gas, probably takes place simultaneously. Substrate in which the migration terminus is asymmetric gives the product the inversion of configuration suggests that this is following the SN2 type of mechanism and SN2 type of displacement of leaving group by the migrating group. While the apparently has not been demonstrated for the phenol rearrangement as such. It has been shown in the deamination of optically active aminohydrin. This is the aminohydrin which is treated with the nitrous acid. It leads to the formation of diazo compound. This diazo compound eliminates the nitrogen gas and the simultaneously migration of the phenyl group. This phenyl group is migrating from this position to this position. That leads to the formation of a new carbocation, which is more stable than the previous one. Then it undergoes the elimination of proton from the oxygen. That leads to the formation of a carbonyl compound. That phenol is generated. Next, another one, cis 1, 2 dimethyl cyclohexane 1, 2 dione is undergoing the phenol rearrangement. That leads to the formation of 2, 3 dimethyl cyclohexanone derivative is generated. 2, 3 dimethyl cyclohexanone derivative is generated. Next, trans 1, 2 dimethyl cyclohexene 1, 2 diol is undergoing the phenol rearrangement in terms of acid that leads to the formation of a rearranged product is generated after formation of stable carbocation. then 1-methyl, 1-acetyl cyclopentane derivative is generated. 1-methyl, 1-cyclopentyl acetyl derivative is generated. Then 1,2-diphenyl, 2, 1, 1, diphenyl, 2, 2-dimethyl, 1,2-diol of ethane, right? Which is on protonation that leads to the formation of carbocation. That carbocation is undergoing rearrangement that leads to formation of benzylic carbonium, more stable. That leads to the formation of major product. Is like that. But when you understand that, if you believe that the tertiary carbocation is not generated because after rearrangement is involving the H plus ion is attached with carbon, C plus ion is attached to OH group, is more stable than the benzyl carbocation. Okay, benzyl carbocation is more stable. This is only more stable one that leads to the migration of methyl group. That migrated methyl group becomes this major product. In such case, if you look at here, this phenyl group is not undergoing migration. Trityl carbonium is less stable. Tertiary carbonium ion is less stable. When you're comparing these two intermediate, this is the tertiary carbocation, this is the benzylic carbocation. Benzylic carbocation is more stable. Due to that reason, the reaction path is selecting to the formation of this major product. Migratory aptitude. When the two possible reaction sites are chemically equivalent, there is a two centers are there for reacting. Those two are equal for chemical reactivity. The relative age with which a group migrates from the migration origin to the migration terminus is called migratory aptitude. That means that is decided by the one by other. That is called migratory aptitude. For example, a symmetric tetra-aryl phenol of this type, tetra-aryl phenol, the rate of the two ketones formed by the migration of the group aryl or aryl prime maybe takes place major migratory aptitude of aryl and aryl prime group. Both are aryl groups. Then the migratory aptitude depends on the structure of this aryl group. The migratory aptitude of the phenyl is fixed as 1. The phenyl is fixed as 1. This is the 1. Migratory aptitude is compared with if the methoxy group is present at the para position of the phenyl group, it is 500 times more reactive, 500 times more undergoing the migration. At the fourth position is methyl group is attached, then 16 times then the phenyl group it is more reactive, more undergoing the migration. At the phenyl group is there at the fourth position, 12 times faster. When you compare the phenyl with the electron withdrawing groups like chlorine or the electron donating group at ortho position, it increases the stericness. Due to that reason, the reactivity or migration rate is decreased. Next, acid catalyzed rearrangement of carbonyl compounds. Acid catalyzed rearrangement of carbonyl compounds. The secondary or tertiary aldehydes are undergoing this kind of rearrangement. In this rearrangement, isomeric ketones on treatment with the concentrated sulfuric acid, diphenyl acetaldehyde rearranged to phenyl benzyl ketone. Diphenyl acetaldehyde is with treating with the concentrated H2SO4. It is undergoing the rearrangement that leads to formation of phenyl benzyl ketone, desoxy desoxybenzoin is generated. When you coming to the mechanism of this reaction, first the proton elimination takes place at aldehyde carbon. No. Protonation takes place at oxygen of the aldehyde oxygen. Then it leads to the formation of carbon cation. That means the aldehyde carbon is converting into carbocation. Then it is undergoing the phenyl group migration, that is 1,2 shift of phenyl group, that leads to the formation of benzylic carbocation. This benzylic carbocation is more stable. Then elimination of proton, that leads to the formation of C double bond C olefinic derivative generated, which is further rearranged to produce this carbonyl compound. Alpha hydroxyaldehydes and alpha hydroxy ketones undergo similar arrangement under the relatively mild conditions. This is the alpha hydroxy ketone is undergoing the alkyl rearrangement, acid catalyzed carbonyl compound rearrangements. This is the alpha hydroxy ketone. This alpha hydroxy ketone in presence of acid that leads to the formation of migration of this is first protonation is takes place, then methyl group is migrating to here. Methyl group is migrating here. Then it leads the carbocation is generated. Then oxygen is donating to the speed of electron to the carbocation that leads to formation of carbon oxygen double bond. This is the rearrangement and elimination of proton that leads to the formation of this carbonyl rearranged product. Next, some aromatic compounds. Look at here for the rearrangement. Next, Wolff rearrangement. The Wolff rearrangement is an important step in the adenate ester synthesis. Adenate ester synthesis. Wolff rearrangement consists of the conversion of an alpha diazo ketone into ketene, elimination of nitrogen by the elimination of nitrogen gas. The rearrangement is carried out either by heating in solvents or with catalysts like silver oxides. As SL carbene is the intermediate in the olefin. Previously we discussed about the carbene intermediate. The same carbene intermediate is involved in this reaction. Wolff rearrangement, diazomethyl ketone, which is on heating, nitrogen gas will be released along with the formation of SL carbene. This SL carbene is further undergoing the rearrangement that leads to the formation of ketene. That ketene rearranged by reacting with water and undergo rearrangement that leads to formation of higher membered carboxylic acid. The number of carbons are increased. The ketene is converting into acid in the presence of water. The loss of nitrogen occurs rather before the migration of group or for one of the product. Sometimes hydroxyketones, this hydroxyketones is undergoing that reaction that leads to formation of this hydroxyketone is generated. Right. The following evidence support for the mechanism. The carbonyl carbon in the diazomethyl ketone becomes the carbonyl carbon in the acid as undergoing the has been by C13 labeling studies. By undergoing by inserting the isotopes, C13 isotopes, we can study the mechanism. A chiral group migrates with the retention of configuration. The acid obtained by the adenate ester synthesis was degraded to the original acid by the Barbier-Wieland degradation. The acid thus obtained was found to have the same configuration as the original acid. This is the Barbier-Wieland degradation. Look at here. In this case, acid is oxidized. First acid is converting to acid chloride that is treated with diazomethane and that is undergoing the esterification. Diazomethane is attacking on that acid chloride that leads to the formation of diazomethyl ketone. This diazomethyl ketone is treated with silver ion in water. Adenate ester synthesis homologation that leads to the formation of ketene. That ketene is reacting with water that leads to the formation of carboxylic acid. That is the higher homologous acid, which is subjected to the Barbier-Wieland degradation from here onwards to here. That is the Barbier-Wieland. In that procedure, first esterification takes place. That acid is converting into ester. A methyl ester of that this acid is generated. This acid with a ester further treating with the Grignard region, that is phenyl magnesium bromide, that leads to the formation of 1,2-diphenyl alcohol is generated, which is on heating, hydrogenation takes place, that C double bond CPH. This fragment is generated, which is further oxidation with the chromic oxide that leads to the formation of the initial starting material. The formation of the homologous acid is confirmed by the conducting this Barbier-Wheeler degradation experiment, by which it is again converting into starting material. That clearly indicates that this adnet ester involving in the extension of the number of carbons in the acids. That means lower membered carboxylic acids are converting into higher membered carboxylic acids. Next, Baeyer-Williger oxidations. Baeyer-Williger oxidation, ketones are converting into esters. Ketones are converted into esters by using the paracids RCOOH. These are known as paracid. These are the paracids. RCOOH is known as paracid. This ketone is treated with paracid that leads to the formation of an ester. That means simple NS oxygen is inserted between the carbon and alkyl group. This ketone alkyl group, in between the ketone alkyl group, we are inserting the oxygen. The rearrangement involves in migration of a group from carbon to electron deficient carbon. The mechanism, the rearrangement mainly involving insertion of that oxygen, electron deficient oxygen between the carbon and the alkyl group. First, the mechanism involved in that the ketone is interacted with the proton in the presence of acid. That protonation of that carbonyl oxygen takes place. That gives the partial positive charge on the carbon and a partial positive charge on the carbon. Then it is undergoing the oxidation with the acids. This is a slow step, and followed by the hydrolysis that leads to the formation of hydroxy ester is generated. Then further it is rearranged to produce ester. The rate determination step has been shown. This is the rate determining step. Acid catalyzed addition. This clearly indicates that this is a slow step, and it indicates that is the acid catalyzed step of the paracids to the per the ketones. Most probably the loss of carboxylate ion and the migration of R are concerted. This reaction is concerted reaction. The above mechanism is supported by the observation that the labeled carbonyl oxygen of the ketone becomes the carbonyl oxygen of the ester. When for understanding the mechanism, we are labeled this oxygen with the isotope of oxygen 18, which is conducted to the oxidation with the paracids. Then the ester, whatever the ester generated, is also containing the carbonyl oxygen is 18. Therefore, there is no detachment of the carbonyl oxygen on the carbon bond. This Baeyer-Williger reaction in intramolecular rearrangement, and it takes place the retention of the configuration of the migrating group. This is the intramolecular rearrangement. Look at here. This is treated with paracids. That oxygen is inserted between this sigma bond and carbon. Right, that leads to the formation of optically active compound. Optically active compound. From optically active, and also it is optically active. Its optical activity is retained. Next, it is inserted between these two in the sigma bond. In unsymmetric ketones, the rate of reaction is accelerated by the electron releasing group in the ketone and by electron withdrawing group in the paracids. If the electron withdrawing group present in the paracid, electron releasing in the ketone enhances the rate of reactions. The unsymmetrical ketones, the migratory aptitude of the group is following order. Tertiary alkyl group is having a more migratory aptitude than secondary alkyl, and then aryl, and then benzyl. These three are more or less having the equal migratory aptitude than the and more than the primary alkyl and methyl group. Even a bridge-head tertiary alkyl group migrates in presence to the phenyl group, Other examples of migrate Bayes-Liger oxidations is so many. Ketene undergoing double oxidation that leads to formation of dialkyl carbonate is generated. Then it is diketone is also undergoing the Bayes-Liger oxidation that leads to formation of an acid anhydride is generated. Camphor is undergoing the Bayes-Liger oxidation that leads to formation of S, mm, acylation or benzylation product which takes place. After that, it is undergoing cleavage or say, extension of that ester formation is takes place that leads to the formation of a normal product and abnormal product. Both will be generated. These are the apocamphor. This is the apocamphor which is treated with paracin that leads to the formation of a normal product and an abnormal product. In this case, abnormal product is more percentage than the normal product. Okay. This is about the Bayes-Liger oxidation. Okay, we'll continue next week. Thank you.